Let's say you work in a lab and you are interested in analyzing some kind of chemical reaction, and you know that a mole of A is going to react with a mole of B, and we're going to form a mole of C and a mole of D. And the question that you have is whether or not this reaction will happen on its own. Do you need to supply energy to this system in order to get it to happen? And so what you're really asking is whether or not this reaction is exergonic. And if it's exergonic, it means that it's spontaneous. It requires no input on your end, and it will happen. Now, answering it will happen does not tell you anything about how quickly it happens. So in this case, all we can tell by analyzing the Gibbs of reaction is whether or not something is possible on its own. And with that out of the way, to actually move forward with calculating the Gibbs of reaction, what we'll do is turn to a thermodynamic property, which tells us that the standard Gibbs of formation, delta G prime naught, is equivalent to minus R, the ideal gas constant, times the temperature, which has units of Kelvin, times the natural log of the equilibrium conditions of your reaction. And so in this case, we would let KEQ be equal to the concentration of your products, so C, concentration of D over A and B. And it's very important to note that this is at equilibrium. So you're going to walk away from your beaker after you mix 1 molarity of A. You create your solution to have exactly 1 molarity of A, B, C, and D for each species. And you walk away, give it enough time, you come back, you perform the titrations or whatever else you need to do to figure out the concentrations that exist in your beaker, and that tells you your equilibrium conditions. And with those equilibrium conditions, you now can derive what KEQ is. And so once you know what KEQ is, now you can turn to this relationship here to calculate what your Gibbs of your standard Gibbs of formation is. And it's also important to note that your conditions are held constant. So this prime naught here indicates that we are operating at a pH equivalent to 7, a pressure of 1 atmosphere, and initial concentrations of 1.0 molarity for all species. So that's what makes delta G prime naught, the standard free energy of formation, very specific. And because of its specificity, it allows us to tabulate it. And so you don't actually need to do this. So in a textbook, you would just look up the standard Gibbs of formation of some reaction. And so if this is a brand new reaction, you might have to do this on your own. But for most reactions, this already exists. And so now that you've weighted and you've gotten your KQ and you've gotten your delta G prime naught, the next question you have is whether or not this reaction is happening in a cell spontaneously. For instance, maybe ATP hydrolysis needs to be coupled to this reaction in order to push it forward because it might be an endergonic, non-spontaneous reaction. And so the question is, how are you going to determine that? And so what we'll do now is define another property or relation that tells us that the standard, that the Gibbs of reaction is equivalent to the standard Gibbs of reaction, delta G prime naught that we've just defined, plus ideal gas constant times the temperature times the natural log of this constant called Q. And Q does not necessarily equal K. Q is the concentration of your products over concentration of your reactants at some time t, or at some state. So in the case of a cell, for instance, we're not going to be operating at equilibrium because that's pretty boring. Nothing's going to react. And the way you can prove this is once we've reached equilibrium, your delta G will go to 0. When Q is equal to KEQ, you'll get the negative of delta G prime naught, and I'll plug this in just to show you guys. So this does not necessarily equal KEQ, but when it does, delta G is equal to 0. So intuitively, what this is telling you is that you have some kind of reaction occurring in a steady state process, for instance, in the cell or in a chemical reactor, and you're not going to have the equilibrium concentrations of these species, so Q does not equal KEQ, which means that there might be a spontaneity factor involved. And just to kind of further underline this point, when Q equals KEQ, we can substitute Q in here, and what we have is delta G prime naught plus RT ln KEQ, which we already described this to be the negative of delta G prime naught. Therefore, this is equal to delta G prime naught minus delta G prime naught, which is equal to 0. And so that's how we know that when Q equals KEQ, there's no longer a spontaneity factor to our reaction. To wrap things up, so just to consider intuitively what these parameters mean, let's think about what happens if KEQ is a very large number. What does that tell us? It tells us that our products are going to be favored over our reactants at equilibrium. So we're going to have more products than reactants at equilibrium. And if we have more products than reactants at equilibrium, that tells us that first and foremost, our delta G prime naught is going to have to be a negative value, because as we recall in our definition, if KEQ increases, the natural log of KEQ is directly proportional to KEQ, delta G will become more negative. So we can very readily see this, and the more negative something is, the more spontaneous it is. However, if we know that Q is very large, it tells us nothing about the equilibrium conditions. Therefore, it tells us nothing about the Gibbs of formation of our, or the relative Gibbs of formation of our products and our reactants. Okay, and so again, just kind of the overall thermodynamic theme here is that nature is operating to minimize the Gibbs free energy. We want to minimize the free energy of a system, and that's the reason why reactions are spontaneous in the first place, is because the products are more stable thermodynamically than the reactants. Now, the important thing to note here, which kind of alludes to future topics in thermodynamics, is how we get from our potentially unstable reactants to our products involves jumping over some energy barriers, specifically some activation energy barriers. And so if those activation energy barriers are very high, that tells us that the kinetics of this process are going to be very slow, because finding a pair of molecules with sufficient energy, in this case, we need to find if C and D are a lot more stable than A and B, but there's a very high activation energy. It's going to take us a very long time to find a pair of of A and B colliding with enough energy to jump over that activation energy barrier to actually become the more stable products. And so that's where kinetics comes in, and that's where thermodynamics also is very important and cool. So I hope you guys find this useful. Let me know if you have any questions, and thanks for watching.